let's get to the point where we talk about what you and your people are doing and where you're injecting value in this entire process.
Yeah, and I think if we do that, the first thing we have to start with is quantum computers, Alex.
Okay.
So we are Q-Secure, and our job is to provide post-quantum cybersecurity, which means security that is resilient against quantum computing attacks. But before we get there, we have to understand what a quantum computer is and why it's so lethal. So if we go back in history, the compute platforms that we use, the one that we're using right now, the ones that are servers, large server farms, it doesn't matter wherever, satellites, they all use the same. It's called CMOS technology, and it's what we know are zeros and ones. So, back in the 60s, people figured out, well, if we use a 0 and we use a 1, we can program with that. We can use combinations of those to get things done. Now, that served us very well. Obviously, this call is working, and we've had good progress. However, there's been a lot of pressure recently as AI is getting pushed, as data is getting created. I think we create more data every year than we did in entire human history. Data is just abundant, right? IoT is ballooning out, right? You've got billions and billions of sensors and video cameras and every bit of IoT out there in systems. But the problem is the chipsets that we have under CMOS, the ones that Intel make, that AMD make, et cetera, these things are running out of steam. And Moore's law is no longer in play. Moore's law was when the power would double and the price would halve every 18 months. It's not happening anymore. The reason is the electrons on the chipsets they're making them so small, the electrons interfering with each other. Now the heat exchange is happening and they're not able to get the efficiencies they used to get. So we're running into something where we needed a new form of compute anyway. So let's talk about quantum computing. So quantum computers are based on subatomic properties. So remember, CMOS is zeros and ones, but quantum computers use things called superposition and entanglement. Now, if you do any studying in theoretical physics, which is the physics that we call our world Newtonian. So this computer that I have right here, this desk, us as people, we could sense these things because we could touch them and we could feel them, and then we have our senses as well. But at the subatomic level, these things don't even exist. In fact, the double slit experiment proved that nothing really exists at all, only in the sense that we make it exist. And I know that's weird, but look it up.
Well, I'm a big fan of the pilot wave theory myself. So,
there you go. Yeah, wave particle duality. It gets crazy at the subatomic level. Absolutely crazy. You could never dream of the stuff that happens down there. Yet it all propagates into a world that we can, transact, we can move around in, we can exist in. So that's a whole separate conversation. You and I will need to have some beer in Munich to figure that out. But I saw about 5 years ago, I saw that companies were building computers based on these subatomic properties. And I thought, well, wait a minute, why are they doing that? And I saw the CMOS thing and how, that we were losing our Moore's law. And then I thought, okay, well, wait a minute, let's see how these work. And then a company called D-Wave actually commercialized one. And I thought, wow, so they're commercializing a quantum computer. And the subatomic property is really interesting, superposition being the first one. What superposition means is that instead of being in the state of 0, 1, it can be in any and all states at the same time. And that's this wave particle duality. So when something's in a wave function, it can be anything and anywhere. There's no location. That when you take subatomic particles, you leave them in superposition, and then you're able to line up these particles, and we call entanglement, which means that they all are behaving together. You can run a transaction, you can run a process, a compute process. And what you get out of that is you get an exponential effect. So in other words, Alex, if you had 50 servers in the server room and you added one more, you'd have 51. And if you added one more, you'd have 52 servers. But if you had subatomic particles and you have 50 subatomic particles running a process, we add one more, you have 2 to the 51st, then you have 2 to the 52nd. It's exponential. And this is why quantum computers have so much promise, because the power that they have is going to be amazing. Think of that game we used to play as kids where I'd say, hey, Alex, you want $150,000 right now, or you want a penny doubled a day for 30 days? And most people take the 150, right? It's cash up front. Well, a penny doubled a day, it doubled each day for 30 days is $5.5 million. And that's, you think about that. Well, how does that happen so fast? It's exponential. And so when we look at quantum computers, and right now we're in the 100 qubit era. So we got companies like Google and IBM, PsiQuantum, IonQ, Rigetti, all producing computers that have 100 qubits or better, moving to the 2 to 300 qubit era. That's 2 to the 100. Do that math sometime and see how many zeros are at the end of that thing. It gets really big. In fact, to give you one more perspective, 2 to the 300th, which would be a 300 qubit computer, would have more capability of processing units than there are atoms in the entire universe. Fathom that. To just one computer at 2 to the 300. So we're moving into an era now where these computers have amazing power. They're still early, so let's not get over our skis here. But with this power, you can do amazing things. Multivariate problems, so problems that have a lot of variables. That's what these computers crush. Weather prediction, genomics, protein folding, chemistry, where you have to analyze all of in a molecule. You have to analyze all of the interactions of the electrons. That's why new materials are so hard to create. Optimization, of financial, right? Running Monte Carlo simulations in financial crushes classical computers. Quantum computers do like that. The one thing that this leads to is that quantum computers are very good at hacking, because our entire internet is based on a single transaction, which is solving for a factor, right? Two numbers a factor into a larger one. That cannot be done by classical. It's super hard. But quantum, because of all the variables we talked about, absolutely destroys it. So we are in a train wreck right now where quantum computers are heading right towards all of our encryption. And this will force the largest upgrade cycle in computer history. I'm going to stop there because I probably unloaded way too much.
No, actually, that was quite enlightening. I mean, I knew a lot about that aspect from the hardware side myself. And I'm glad you brought it up for our audience, because you're the guest here. And frankly, I think the more you put it into context, the better it is for all of us. So yeah, I'm glad you went over it. And now we can go on to how you apply your solution with everyone on the same sheet of music.